Hi! Today we're going to learn about finding the area under, or finding the formula to the area under polar curves. So, what are polar curves? Well, it's a different type. So polar coordinates are a different type of coordinate system than the Cartesian plane. So instead of being rectangular coordinates, which is x, y, polar coordinates are written as theta, r, or angle, radius. So, and polar coordinates are written with r is equal to some function in terms of theta. Could be r is equal to 5 theta. But we don't need to have theta there. So r is equal to 5. That's similar to x is equal to 5. But x is equal to 5 would be a line. In our case, r is equal to a constant makes a circle. In this case, r is equal to 5 makes this circle here with radius 5. So, and in this video we're going to use this as our basic example. So polar coordinates makes it very easy to graph curves that are harder to graph on that we can't graph on the Cartesian plane, such as a circle. We can't graph a full circle with one function on the Cartesian plane. However, with one function, we can do that on a polar coordinate system. But that does make it different when you're trying to integrate it or find the area under the curve. In this case, we just want to find the area between the curves. So we just want to find this entire area here, which is between the curves or in the curve. So how do we do that? Well, we know that the polar coordinate system always starts from the central point, 0, 0. So this point here, well, let's just say this is in this function r is equal to 5, the center point does line up with the origin, which would be 0 theta, 0 r. Or just 0 r, because 0 r is equal to 0 would just make that dot. So, how do we do this? Well, let's just take this example of a circle. Now, in a regular Cartesian plane, we know that to find the area under the curve we would do integration, which would mean we'd be taking an infinite number of infinitely small rectangles and adding up the area. However, that's a little harder when you have, or that's harder to do when you have a function that models curves. So it's hard to find the y-coordinate when there is no y-coordinate. You just have theta and r. So what do you do? Well, what we can do is we can find an area of a sector and make an approximation like a Riemann sum, but instead of having rectangles, we could have sectors. So that means that, let's take a closer look at this example. So, to find the sector, let's just say we're finding the sector of a circle. To find the area of the sector, we would do the angle measurement, or theta, over, let's do this in radians instead of degrees, 2 pi, because 360 degrees, or one full rotation of a circle, is 2 pi radians, times the area, pi r squared. Now, we can do this with any curve, even if it's not a circle, because you're just taking that one small sector. So if you just take that one small sector, let's say the function was like this, and if you're just taking the area of this sector here, you can make this circle, sorry, this isn't really a circle, and just take the area of this sector. So even if the graph is not a circle, you still use this formula, because you can take that small section that you would have, make a circle around it, and find the area of that sector. But that's just finding the area of one sector. Let's say we wanted to find the area under this complete curve. And this isn't really a polar curve, but let's just imagine that it was. So let's say that it was a different one, not a circle. Let's imagine that we had this graph here, and we had this function. And let's say that we wanted to find the area from here to, let's say, from angle, and this is sort of like our x coordinate, so let's say we want to find it from theta is equal to 0 to, let's say, theta is equal to 2 pi. Then we would have the area of this, which is sort of the area under the curve, or between the curves. So how do we do that? Well, once again, let's erase this part inside because that makes it harder to see. So once again, we make these small sectors. We make a circle out of these sectors and just find the area of these sectors, and then add them up, all the infinitely small infinite sectors from 0 to 2 pi. So that's how we would do it, right? Because that's how you do it with the Riemann sum, but instead of having rectangles, you just have sectors. But how does that change when we have our formula? So how does that implement itself into our formula? Well, first of all, we can see that the pi's will cancel out. So this function is, so far, angle theta over 2 times r squared. But if this is an infinitely small sector, then that means that the angle is infinitely small too, which is d theta over 2. So instead of theta, we have d theta, which is an infinitesimally small amount. So in this case, it's an infinitesimally small angle over 2 times r squared. But that's just for one infinitesimally small sector. How do we do that when we have an infinite amount of sectors? How do we calculate, or how do we add them all together? Well, that's simple. We just have the integral. So the integral will add up all of them together. So we have the integral from a to b, which are theta values, of, let's just rearrange the terms. So r squared over 2 d theta. So now we can solve this integral because, or it should have been dr, or it's d theta. And we have r squared over 2 d theta. Now we can't really solve this integral right out of the box, right? Because it's in terms of r, but we have to, because we have r here, but we're trying to solve the integral in terms of theta. So how do we do that? Well, we know that r is always r is a function that's always in terms of theta. So it could be r is equal to 5, or r is equal to cosine 2 theta. But r is a function, and in polar curves, r is a function that's in terms of theta. So it's simple, we just substitute whatever our function is in for r, because that's what r is equal to. So let's do this example over here. We know that this area will be pi r squared, or 25 pi. Let's just write that up here. But let's see if our formula works, because we know that a circle can also be modeled as a polar curve. So this would be equal to, this circle is r is equal to 5, so the integral from what to what though? Well, we know the circle is just one full rotation, which is 0 to 2 pi radians. So 0 to 2 pi r squared, or 5 squared, which is 25 over 2 d theta. So this can be rewritten as 25 over 2 times the integral from 0 to 2 pi of d theta. And so take a good look at this first part here, because now we're going to erase it and go up there. Now we're going to move up here. So 25 over 2 times the integral from 0 to 2 pi of d theta becomes 25 over 2 times theta evaluated from 0 to 2 pi, which becomes 25 over 2 times 2 pi minus 0. You can just take this part off. The 2's will cancel out, and that gives us 25 pi. 25 pi. So the answer is correct. It matches up with the area of the circle. But the real answer to this problem, which is finding the formula for the area under the polar curve, is the integral from a to b of r squared over 2 d theta. Today we learned about how to find the formula for the area under polar curves.